Well, greetings, mathletes, and welcome to the first lecture of fall 2020. Um, so we're going to talk about probability today, and I'm going to line up some of the nomenclature, the jargon, or the technical vocabulary. We'll do that first, and then we'll just jump right in and look at some examples and see how those definitions and ideas apply. So let's go ahead and get started. So we're talking about probability. Now, if I want to talk about the probability of some thing occurring. So let's say A is an event. Okay. Um, P of A, right? This is how we write the probability of A occurring. Ooh, running out of room there. Um, right. So that's the notation. That's the mathematical notation. So if oh, I don't know. You can write this stuff a lot of different ways. I could write things like the probability that x is equal to 3. That's actually a thing that you can write because x could equal 3. That's a thing that could happen. So you can compute its probability. Um, you can have the probability of drawing a male student from a basket of all of your students. That's certainly a legitimate thing to do. Sometimes you're doing things like drawing marbles out of a bag, and you want the probability that the marble is red. So a lot of the time that just gets written this way, right? So that P with the parentheses around it tells you that that's what you're computing the probability of. Hey, that looks like a function, Mr. Ryan. Yeah, it does look like a function, and that's actually because it is. The input is the event that you're calculating the probability of, and the output is the numerical probability of that happening, right? So if I'm talking about the probability of x equals 3, if I don't know if there's just a 50-50 chance of that happening, um, I could say that the probability is zero point 0.5, right? It just depends on the situation. So we'll talk about how to compute those probabilities here in a second. So let me go ahead and get rid of this. Okay, now, so how do you mathematically compute probability? Well, the formula for that looks like this, right? The probability of A occurring is equal to n of A divided by n of S. Yeah, and without knowing what any of these things mean, it still doesn't mean anything. You know that it's a probability. But here's the idea. Um, the function n, if I'm talking about n of anything, right? And I'm just putting x as just a dummy variable because you can put anything in there. What this is it's called the cardinality. And the cardinality is basically the number of things in that set. So A is a set, S is a set, right? A would be the set that contains all the things. Um, oh, I don't know. It depends on what the trait is that you're measuring. If you're talking about measuring how many female students there are, um, n of well, if F is the set of all female students, then n of F would be the number of female students. So the cardinality is the number of things in a set. And I should say in this case, an event, right? Or you can think of it as the number of ways an event can happen, right? If X is an event, then n of X is the number of ways it can happen. And we'll talk about what that means here in a little while. So if we know that, the only thing we further have to figure out is what S is. Now S, let me do this real quick, get rid of this. There we go. S is pretty universal at this point. It's called the sample space. And the sample space is the set of all possible outcomes of a procedure. Right? So basically what this formula is saying now, if I want to know the probability of A occurring, I find the number of ways A can occur and divide it by the total possible number of things that could occur. Um, so let's see here. We got that. We got that. Yeah, and we'll continue from here. I'm going to actually at this point, um, I think we have all the definitions we need. So what I want to do now is clear this out. So let's go ahead and clear this out, and we'll look at an example of how this applies. So we'll go ahead and delete that, and delete that, and okay, and boom. Okay. So here's a typical deck of cards. These are always fun to play with for probabilities because there's so many different ways that you can divide these things up. You can divide them up by suits, right? I have diamonds, hearts, spades, and clubs as I look at this. That's a really weird way that has there. Okay, yeah. So we have diamonds, hearts, spades, and clubs here. And let's switch that over to a pencil. Maybe that'll be a little better. Anyways, so let's say I want to work on the probability. Oh, that's too faint. Let's darken that up. That's still not dark enough. There we go. Okay. Let's say I want the probability of getting hearts. Right? So I'm looking for the probability of getting hearts. So according to the formula, what I need is the number of ways that I can get hearts, and I need to divide that by the number of things in the sample space. Now, the sample space is every way you can draw one card, right? So if I'm going to draw one card, there are 52 different cards I can draw. So the number of things in the sample space in this case is 52. Now the number of hearts there are, you can actually just go through and count them. If you count them all the way across, you'll see that there are 13 of them. Right? So the probability of getting hearts if I draw one card is 13 out of 52. Now that's a raw probability. Usually you're expected to reduce these fractions. And so this fraction does reduce 13. In fact, you can kind of look at the deck of cards and see what it reduces to actually. 13 goes into 52 4 times. So that means that the probability of getting hearts is 1/4, or if you write it as a decimal, the probability would be 0.25. Right? So that's really straightforward. Right? We want the number of ways I can get hearts divided by the number of ways I can draw a card. Right? It's pretty straightforward. Sometimes counting these things is what's not so straightforward. Okay, so let's go ahead and take a look at another one here. Oh, and by the way, since we had just decided that the probability of getting hearts is equal to 1/4, you'll notice if I just look at this deck, I can see that 1/4 of the cards are hearts, right? It's clearly 1/4 of the whole business. So I guess that's a little lesson in fraction reduction as well. Okay, so let me go ahead and get rid of this stuff. Okay, now, um, suppose I wanted to find the probability that this is a heart or, now the or symbol, when we're talking about, and I'll explain what this means here shortly, we have hearts or a three. Let's say it's one of those two. Now, what this is a union. And what it means is that um, you're going to be counting all the ways that you can get things that's either a heart or a three or both. So if I look at this, I can see that hearts are right here, right? Three is right here. And you notice the three of hearts gets counted in both of these sets. And so we have to be real careful. We have, there's 13 in this row, and then I have four in this row also, but this one's already been counted. So that's actually only three new cards. So that means there are 16 different ways that I can get a heart or a three out of 52. And if we go ahead and just start slicing this down, let's see here. I'm going to just reduce by twos because that's usually the easiest way to go. If I divide them both by 2, it's 8 over 26. And if I keep going, that is 4 out of 13. Right? Okay. Yeah, so we're good there. The thing I wanted to emphasize about this, so this is whenever you use that U symbol, you notice there's no tail on the U either. It's just it's a cup is actually what the symbol's called. If I'm talking about using the union here, and that was actually terrible handwriting. Let me try that again. If I'm talking about A union B, what that means is anything that's A or B. And in math, when you say or, that could mean both, right? So just so we understand what that means in context here. So basically, you're finding all the different ways that either A or B could happen, or they could both happen simultaneously. So let's see here. Let's go ahead and erase this. Get that off of there. There we go. All right. Now another thing we can look at is larger groupings. You know, you can do this a lot of different ways. If you're looking at things like the probability that it's red, right? Well, you know, honestly, once you have the whole sample space out in front of you, like you do with a deck of cards like this, you can almost look at it and see. Um, if you just look at this, you can see that half of the cards are red. So that means the probability needs to be one half, right? You can count them all out and get 26 over 52. And then when you reduce that, you end up with one half because 26 goes into 52 twice, or 0.5, right? So so we can group these things a lot of different ways. And there's different groupings. These guys down here, these are called face cards. Just depending on who you're talking to, sometimes aces are considered bigger than kings, sometimes they're considered ones. It just depends on how things are working. But nonetheless, just understand the dynamics of a deck of cards because there are questions that have to do with that in your homework. So now let's go ahead. We'll get rid of that and we'll take a look at another example. Okay, so our next example here. What is the probability of rolling two four-sided dice and getting an even number? I want to add to that. I probably wrote that a little bit poorly. And getting a sum that's an even number. Let's just add that in. A sum that's an even number. There we go. That's actually what I meant. In any case, I chose four-sided because the sample space is much smaller, so it's a little easier to write the whole thing out. So for one die, for a single die, there's four possibilities, right? Um, you can roll a one, a two, a three, or a four. Um, and then the second die also has four possibilities. The same thing, one, two, three, or four. And then we have to add those two possibilities together. And so um, we have to know how many ways that we can roll an even number, and then divide that by how many ways we can roll two four-sided dice. Yeah. So one of the ways you can do this is just to make a table of all the possible pairings that you can have. So I like to look at it this way. So across the top, I have the outcomes for die number one. And across the side, I'm going to write out the outcomes for die number two. Right? And in the boxes, I'm just going to put the sums. They may not be the neatest boxes, but they're some of the finest things I can draw. Okay, so our sums, let's take a look at them. So I have 2, 3, 4, 5, and then 3, 4, 5, 6, and then 4, 5, 6, 7, and then 5, 6, 7, 8. Okay, so if we want the probability of getting an even sum on our roll of two dice, the four-sided dice. You can see if it's six-sided, I would have had a bigger table here. I need the number of ways I can roll I can roll a sum that's even, divided by the total number of ways that I can roll the dice. Period. Okay, so let's go ahead and count all of our even stuff. So we got 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 different ways to roll an even sum. Okay, and then now we need the total number of ways that the die could roll. Period. So that means everything included. And if you count these up, you can see there's 16 boxes here. So it's 8 out of 16, which means the sum being even has a 1/2 or 0.5 probability of occurring, right? Now, we can ask other things too. That first one was just the probability of it being even. Um, what about the probability that it is not 3? Okay, so now we have to count all the things that aren't 3. Now, when it comes to these kinds of statements, there's different ways to say not 3. Um, one of them, all of these things say the same thing, by the way. So I want the probability of not 3. That's one way I've seen it. These are all things I've seen in textbooks. I've seen people use the tilde, right? The little squiggly line. And I think this would get confusing with numbers. But sometimes it's usually more done with sets when you have a letter or what have you. But oftentimes the line over the top means not. So if I put a line over A, that means not A, right? So things that are in the sample space but are not in the set you're talking about. So let's get rid of some of this stuff here, right? So if I want the probability that this is not 3, I need all the different ways I can add up that do not equal 3. Well, I know there's only 2 3s in the whole thing. I can see them right there. And I know there's 16 altogether. We counted that from the last problem. So that means there has to be 14 things left that aren't 3s. I don't even have to know what they are. I just need to know there's 14 of them. And that reduces to 7/8. Right? And if I'm not mistaken, that would be 8.875, I think. I think that's what that comes out to, because 8/8 would be 1. Yeah, so that would be 0.875. So yeah, sometimes you have to actually go in and write out the table yourself, make sure you have all the pieces counted, and then just go through and count them. Um, so for the first one, we had the deck of cards that was already pre-done, right? We had that table out in front of us. We could look at it. Um, the In this case, we were just given the situation. We were told we had two four-sided die, and we had to make the table ourselves. So sometimes you have to organize things on your own. And the last thing here I want to talk about is this idea of the expected value. Okay, so there's a big difference between what the expected value is and what the actual value is. The expected value doesn't even have to be a possible value. It's just it kind of has to do with what the probability says. So here's an example here. Uh, so we have a guy. We got when aiming at the bullseye, a darts professional has a 0.72 chance of hitting his target. So almost 3/4 of the time he hits the bullseye. If he throws a dart at the bullseye 90 times, what's the expected number of bullseyes he'll hit? Now, before we even tackle this, I kind of want to simplify this down to something that you can probably picture. You may even have the tools in your pocket to play this game. Um, but, if you flip a coin, which is a very common probability thing to use, um, if I flip a coin 10 times, right? If I asked you how many times would you expect to get heads in those 10 times, what would you say? I'd say 5. Okay, so how did you get 5? Um, be, uh, it's a good question. Well, it's 50%. Yeah, it is 50%. Well, that's half. Right. So what did you do to get that? Well, I took half of them. That's right, you took half of them. And what that actually is multiplication. So what you did is you took the probability of something occurring and you multiplied it by the number of times it occurred. And in this case, you got 5, right? And so in general, if you have n trials, then the probability, well, let's write that a little bigger. The probability of, that's not what I wanted to say either. Let's try this again. In n trials, the expected value which of A, which is written quite oftenly E of A, is equal to the number of trials times the probability of A occurring. Okay, so you take the number of times you're trying something and you multiply that number by its probability. So if we're going to look at this over here, let's see here. How many trials do I have? Let me get this off the thing so we don't distract. How many trials am I going to have? Because what I'm looking for is um, the expected number of bullseyes. Right? That's actually what I'm looking for. So the expected number of bullseyes is going to be the number of trials times the probability of getting a bullseye on one trial. So from there, I know I have 90 trials, right? And the probability of a bullseye is 0.72. And if we just go ahead and calculate that, well, oh, good, I did put a calculator around here somewhere. So I got 90 times 0.72 Oops, I didn't hit times. Let's try that again. Times 0.72. That gives me 64.8. Now, if we think about this and we just use our common sense, can you hit 64.8 bullseyes? That means if I throw it 90 times, I should hit 64.8 bullseyes. No, that's not what that means at all. Um, what that means is if I did a bunch of trials and I took this same person and I had them throw 90 bullseyes a bunch of different times. So today you throw 90, tomorrow you throw 90, next year you throw 90. You keep doing that every day for a long, long time. And you average the number of bullseyes you get every single day. That number will get closer to this number, is what that's saying. And that's actually what's called the law of large numbers, which says the more times you run an experiment, the number of results should the number of successful results should approach the expected value, right? So that's the idea. An expected value does not have to be a value that you can attain. Because how do you get zero point 0.8 of a bullseye? That doesn't even make sense. What it's saying is that it should be near that number, is what it says. In fact, it's very possible that you never actually hit the expected value. That's a pretty common thing. So, um, in any case, that's actually the last thing I wanted to wrap up was talking about the expected value, and um, from there, where's that button? There it is. I did want to tell you something funny though. I noticed the name of this course is very, very large, the basic structure of mathematics. Um, and so I thought I'd abbreviate it, but it turns out that BS math probably sends the wrong message.